Today we are going to talk about semiconductor photodetectors. Here are the topics that we covered in the previous lecture. Today I will first introduce you to photodetectors. Then I will talk about direct and indirect bandgap photodetectors. Then we will discuss semiconductor photodetector parameters, or we can also call them semiconductor photodetector figures of merit. Then I will discuss semiconductor photodetector types, and finally we will talk about photodetector noise. But photodetector actually is a really comprehensive topic. So instead of covering it in just one lecture, I decided to cover it in 2 lectures. So today we will mostly talk about the first 3 bullet points, and then we will partially cover semiconductor photodetector types as well. But mostly we will cover the final 2 bullet points in the next lecture. The research and study on photodetector requires a lot of facilities, from modeling to epitaxy and deposition. And after deposition of the films, we need to characterize the films using different characterization tools. Then fabrication of the devices is required, which also involves photolithography and contacts deposition. And finally, it requires device characterization. Here at our Center for Advanced Electronics and Photovoltaic Engineering, we have all the relevant facilities required for doing research on photodetectors. And currently, various students here at our Center for Advanced Electronics and Photovoltaic Engineering are working on zinc oxide on silicon, aluminum nitride on silicon, copper oxide on silicon, and nickel oxide on silicon-based photodetectors. A photodetector is a device which converts light into an electrical signal. So the input for a photodetector is light, and the output for the photodetector is voltage and current. Assume a simple photodetector which actually is a p-n junction. We have the p-type layer on the left and the n-type layer on the right. And we have connected it to a battery. So the positive terminal of this battery is connected to the N side, and the negative terminal is connected to the P side. Essentially, this configuration is reverse biased. And then we also have a resistance in the loop. So when light is incident on this photodetector, if the band gap of this if the energy of the incoming light is greater than the band gap of the semiconductor, this incoming light would result in the generation of electron-hole pairs. The electrons would be attracted by the positive terminal towards the right, towards the n-type layer, and the holes would be attracted by the negative terminal towards the left. And the movement of these carriers would result in a current. This current can be measured by an ammeter, and the voltage would appear across this resistance, and this voltage can also be measured. And the response of this photodetector would be proportional to the intensity of light, or the power in the beam. The applications of photodetector range from media to telecommunication, laser applications, medicine, biology, industry, defense, mining, and there are a lot of physics-based applications as well of photodetectors. Now, photodetectors are made up of semiconductors, and these semiconductors could be direct bandgap semiconductors, or they could be indirect bandgap semiconductors. So far, we talked about semiconductors and their energy band diagrams. We talked about the conduction energy levels, and we talked about the valence energy levels. But so far, we assumed that these energy levels are flat lines. But in reality, these bands, these energy levels are not flat lines. They have variations in the conduction band and they have variations in the valence band as well. Here is a representation of a typical direct band gap semiconductor, where this is an EK diagram, where E represents energy and K corresponds to the momentum vector here in this diagram. So these bands, the conduction band has minimum and maximum levels. Similarly, the valence bands also have minimum and maximum levels. We know that electrons have a tendency to try to settle down at the minimum of the conduction band. So electrons in this structure would try to settle down over here. And similarly, we also know that holes are inclined to settle at the top of the valence band. So in this valence band, holes would try to settle down over here. And we can see in this EK diagram that the minimum of the conduction band for this semiconductor is aligned with the maximum of the valence band. And when this case occurs, we call it a direct band gap semiconductor. And by direct band gap semiconductors, the minimum of conduction band is aligned with the maximum of the valence band. In this case, when a photon is incident on this semiconductor, and if the band gap energy of this incoming photon is greater than the band gap of this semiconductor, it will result in the generation of an electron hole pair, electron transitions from the valence band to the conduction band. And since this transition occurs along the E direction, so it just requires conservation of energy. It doesn't require conservation of momentum, because the transition does not occur along the K direction. It does not occur along the momentum direction. So predominantly, most of the energy of the incoming photon is utilized in the generation of the electron hole pairs. Examples of direct band gap semiconductors are gallium arsenide, indium phosphide, gallium nitride, aluminum nitride, indium gallium nitride, aluminum gallium nitride, indium gallium arsenide, etc. On the other hand, in case of indirect band gap semiconductors, the minimum of the conduction band is not directly aligned with the maximum of the valence band along the E direction. So in this case, when a photon is incident on this kind of semiconductor, it would result in the generation of an electron hole pair. Part of the energy of the incoming photon is utilized in this generation of the electron hole pair, but the rest of the energy is wasted in the form of phonons, in the form of lattice vibrations, which actually results in heating of the device. So for a lot of semiconductor applications, for light emitting diodes, for solar cells, for photodetectors, direct band gap semiconductors are more desired as compared to indirect band gap semiconductors, because in indirect band gap semiconductors we would have losses as well. Here I have listed different figures of merit for photodetectors, or we can also call them the photodetector performance parameters. The first figure of merit is quantum efficiency, which is the number of electron hole pairs generated per incident photons. Another figure of merit is responsivity. It is the ratio of output current to the input optical power. As we know, in case of a photodetector, the input is optical power or light, and the output is current. So responsivity is the ratio of the output photocurrent to the input optical power. Another figure of merit is spectral response range, which is the range of wavelengths over which the photodetector will operate. Response time is the another figure of merit, and it actually measures the speed of photodetectors. It measures how quickly our photodetector device will respond to variations in the input incoming light intensity. Finally, noise characteristics are also important for photodetectors. So in case of photodetectors, the input is optical power. It is light. And we know that there is noise in the environment, and there is noise generated by semiconductor devices as well, thermal noise, etc. So if the power levels of the incoming light are low, our photodetector should still be able to operate properly in the presence of that noise. So noise characteristics are crucial to photodetectors, and we will cover these figures of merit one by one in this lecture. Let us talk about the first figure of merit, which is quantum efficiency. As I already told you, that quantum efficiency is the number of electron-hole pairs generated per incident photons. Consider a semiconductor block as a photodetector. We have incident photons on the surface of this block. This block has a certain thickness, certain length, and certain width. So this incoming light has a certain number of photons. How do you determine the number of photons? You can determine it by a simple equation. It's equal to the optical power divided by Planck constant into nu, or frequency of the incoming light, where nu is equal to c divided by lambda. C is the speed of light and lambda is the wavelength of the incident light. So this gives us the number of incident photons. And according to the definition, so this is the input. Efficiency is output divided by input. This is the input, the number of incident photons. Our output is the number of electron-hole pairs generated. How do we determine this number of electrons-hole pair generated? So this incoming light would result in the generation of electron-hole pairs, and their movement would result in a particular current. That current can be measured across an external circuit, and this current divided by charge on electron gives us the number of electron-hole pairs. So basically efficiency is equal to output divided by input. Output is IPH divided by the charge on electron, and input is light, which is P naught divided by h nu, gives us the number of incident photons. Replace this value in the quantum efficiency equation, and here we get a simple relationship for calculating the efficiency of photodetectors. Another figure of merit for photodetector is spectral response range, which is the range of wavelengths over which the photodetector will operate. For example, for silicon-based photodetectors, the spectral response range is in the range of 400 to approximately 1100 nanometers. For gallium arsenide, it's in the range of 650 to 870 nanometers. For germanium, it's in the range of 600 to 1600 nanometers. Germanium and indium gallium arsenide based photodetectors are mostly suitable for communications, where a wavelength around 1500 nanometers is required. Now, the question is, what determines the spectral response range of these photodetectors? What determines the lower cutoff wavelength? For example, in case of silicon, the lower cutoff wavelength is 400 nanometers. And what determines the upper cutoff wavelength for these different kind of photodetectors? To answer that, let us focus on this simple equation. Our upper cutoff wavelength is calculated using this simple equation. Lambda upper cutoff wavelength is equal to hc divided by the band gap of the semiconductor, where h is the Planck's constant and c is the speed of light. So our wavelength corresponding to this band gap in micrometers would be equal to 1.24 divided by the band gap of the semiconductor. For example, the upper cutoff wavelength for silicon would be equal to 1.24 divided by the band gap of silicon, which is 1.1 electron volt. So the upper cutoff wavelength for silicon would be around 1100 nanometers. So essentially the upper cutoff wavelength is dictated by the band gap of the semiconductor. How about the lower cutoff wavelength for these photodetectors? The lower cutoff wavelength is dictated by the absorption coefficient of semiconductors. Here is a plot of absorption coefficient per meter versus wavelength in the range of 0.2 to 1.8 micrometers. Or in nanometers, it's in the range of 200 to 1800 nanometers. So we have absorption coefficients of different materials. We got absorption coefficient of silicon, gallium arsenide, indium phosphide, germanium, indium gallium arsenide, and other materials, for example. Let us focus on silicon. The absorption coefficient of silicon is high at lower wavelengths. For example, wavelengths in the UV ultraviolet light range, 200 nanometers to 400 nanometers. As you can see there, the absorption coefficient is really high. Then penetration depth or absorption depth is equal to the reciprocal of the absorption coefficient. In order to understand it more, let us go back to slide number 11. We assume that this block is our semiconductor photodetector, and a particular light intensity is incident on this semiconductor photodetector. So this light would be absorbed in a particular depth of this block, determined by the absorption coefficient. If the absorption coefficient is high, as we know, absorption coefficient is high at lower wavelengths, 200 to 400 nanometers. If the absorption coefficient is high, this light would be absorbed in shallower depth of this block or close to the surface of this photodetector. And if the absorption coefficient is low, then it has higher absorption depth, and this light would travel to a deeper distance inside this photodetector. So generally, short wavelength light travels shallower to a shallower depth inside this photodetector, and longer wavelength lights would travel deeper into this photodetector block. Consider silicon. Assume a wavelength of 400 nanometers or 0.4 micrometers. So the absorption coefficient at 400 nanometers is it's more than 110 to the power of 6 per meter. So the absorption depth at this particular wavelength would be equal to 1 over alpha, or it's gonna be less than approximately 1 micrometer. So all the incident light at 400 nanometers would be absorbed around 1 micrometer in silicon-based photodetectors. However, for longer wavelength light, it's going to be absorbed in a deeper depth of the photodetector. So shorter wavelength light travel shallower inside photodetectors, and longer wavelength light is going to travel deeper into the photodetectors. Similarly, we have this expression: intensity as a function of distance is equal to intensity at the surface of the photodetector times exponential of minus alpha, where alpha is the absorption coefficient, times x. X represents depth, which means that the intensity of light actually falls exponentially as a function of depth, as a function of distance inside the semiconductor. Going back to slide number 11 once again, it means that the intensity of light would be maximum at the surface, but it falls down exponentially as a function of depth inside the photodetector. Another figure of merit is the responsivity, is the ratio of output photocurrent to the input optical power. Output photocurrent is represented with IPH, and the input optical power is represented with P naught or P optical. And also, going back to the quantum efficiency equation, to slide number 11, since responsivity is equal to IPH divided by P optical, replace this with responsivity and reorder the equation. We get an equation for responsivity which is equal to quantum efficiency times charge on electron divided by Planck's constant times the frequency of the incoming light. I'll replace the frequency with the c divided by lambda. We get this form for calculating the responsivity of a photodetector. Here we have responsivity curves for different semiconductor based photodetectors. We got responsivity curve for silicon, we got responsivity curve for germanium and for indium gallium arsenide. And from the responsivity curves, we can also determine the spectral width of the semiconductors. Like for example, over here, the spectral range of photodetectors. For example, the lower cutoff wavelength over here for silicon-based photodetectors is around 400 nanometers, and the upper cutoff wavelength is around, like the maximum wavelength is 1100, but we get increased responsivity around at 900 or nanometers or 1 micrometer. We can also determine the wavelength corresponding to maximum quantum efficiency from the responsivity curves, and we can also determine the maximum quantum efficiency for a particular semiconductor based photodetector from the responsivity curves. Consider, for example, the responsivity curves in amps per watt versus wavelength for silicon based photodetector. So here is the responsivity curve given in red, and if we draw a tangent line from origin to the responsivity curve, it touches the responsivity curve at this point. The corresponding wavelength at this point, at the intercept point, is 700 nanometers, and the responsivity corresponding to this wavelength is 0.45 amperes per watt. Now this wavelength actually gives us the this corresponds to the maximum quantum efficiency for silicon based photodetectors. How do you determine the maximum quantum efficiency? If we know the wavelength and we know the corresponding responsivity, just replace the values of responsivity and wavelength into this quantum efficiency equation, and it comes out to be 80%. So the maximum efficiency that we can achieve with the silicon based photodetectors is 80%. Similarly, if we draw a tangent to indium gallium arsenide, the maximum quantum efficiency that we can achieve for indium gallium arsenide based photodetectors would be less than 70%, around 60%. For germanium, the maximum achievable quantum efficiency would be around 50%, and so on. Now, ideally, we should be able to achieve a maximum quantum efficiency of 100%. But what are the factors that result in reduced quantum efficiency for these photodetectors? Let's go back to slide number 11 once again. So once again, we assume light incident on the surface of this semiconductor photodetector block. Now, it's not essential that all the incoming light gets absorbed inside this photodetector. Some of the light would be reflected. So because of that reflected light, we got some loss in efficiency. Secondly, the energy of the incoming photons should be greater than the band gap of the semiconductor. If it is less, it's not going to result in the generation of electron hole pairs. So it is another factor leading to a reduction in the quantum efficiency of these photodetectors. Thirdly, even if the energy of the incoming photons is greater than the band gap of the semiconductor, it gets absorbed by this photodetector block, resulting in the generation of electron hole pairs. But with the passage of time, there is a chance that some of the generated electron hole pairs would get recombined once again with the passage of time due to different recombination mechanisms, due to OJ recombination, due to radiative recombination, or due to Shockley-Red-Hall recombination. So because of these factors, we cannot really achieve an efficiency of 100%. The efficiency for photodetector is always less than 100%. Now let us talk about semiconductor photodetector types. The different types of photodetectors are photoconductor, PN photodetector, PIN photodetector, metal semiconductor metal photodetector, and avalanche photodiode. Let's talk about each one of them one by one. In a photoconductor, we have a semiconductor and two ohmic contacts connected to an external battery and to a resistance or to a load. So when light is incident on this semiconductor, it results in the generation of electron-hole pairs. And here we have the conductivity equation for semiconductors equal to charge on electron times mobility of electrons times the carrier concentration if it is n-type semiconductor plus mobility of holes times the carrier concentration if it is p-type semiconductor. Or it can be an intrinsic semiconductor. In case of intrinsic semiconductor, it's going to result in the generation of electron-hole pairs. So both electron carrier concentration and hole carrier concentration contribute to the conductivity. So the incoming light would result in the generation of electron-hole pairs, and this would result in an increase in their carrier concentration, and an increase in the carrier concentration of electrons and holes would increase the conductivity of this photoconductor, which can be measured across the external resistor. Now there are different types of photoconductors. There could be intrinsic photoconductors and there could be extrinsic photoconductors. Intrinsic means undoped photoconductors in which light, the incident light, results in the generation of electron-hole pairs where the transition occurs from valence band to the conduction band. But the condition is that the energy of the incoming photons should be greater than the band gap of this semiconductor. We could also have extrinsic photoconductors where it could be p-type doped or it could be n-type doped. In case of p-type doped photoconductors, we actually introduce acceptor levels close to the valence band of the semiconductor, while in case of n-type photoconductor, we introduce donor levels close to the conduction band of the semiconductor. So in this case, the transition only occurs from the acceptor level to the valence band or from the donor level to the conduction band. And this gap is really narrow. This is around 30 millielectron volts, 40, 50 millielectron volts. So extrinsic photoconductivity is generally used to detect low energy photons for long wavelengths, for example, for infrared, where infrared means wavelengths above 750 nanometers. Another kind of photodetector is PN photodiode. Here is the structure of PN photodiode, in which we have p-type semiconductor adjacent to an n-type semiconductor, and electrodes are connected to both the p and n-type semiconductor. Then this configuration actually works under reverse biased, and we have a resistance connected in the circuit as well. We would also like to have anti-reflection coating on the top layer of the PN photodetector. As I already told you that some of the incident light gets reflected, resulting in loss in quantum efficiency of photodetectors. So anti-reflection coating actually matches the refractive index of air with the refractive index of the p-type semiconductor, resulting in more absorption of the incoming incident photons, leading to increased efficiency of the photodetector. So why would we operate this configuration under reverse bias? Reverse biasing means that the positive terminal is connected to the n-type semiconductor and the negative terminal is connected to the p-type semiconductor. Why do we connect it in reverse configuration? Because as we know that reverse biasing results in an increased depletion width. And we know that junction capacitance is equal to permittivity of semiconductor divided by the depletion width. So under reverse bias, we have increased depletion width resulting in a decreased junction capacitance. And since the speed of photodetector depends on the RC time constant of the photodetector, where the resistance contribution comes from this external resistance and also from the quasi-neutral regions of the photodetector. So decreased capacitance means decreased RC time constant, resulting in faster response time of the photodetector. So under reverse biasing, this configuration gives us higher speed for photodetectors. Here is a symbol of PN photodetector, and here are the IV characteristics of the PN photodetector. This gray curve actually represents IV characteristics of this configuration under dark conditions, under no light. Under the application of light, when light is incident over here onto the surface of this photodetector, it's going to result in the generation of electron-hole pairs, resulting in an increased current represented by the yellow curve. And if we further increase the intensity of the incident light, it is going to result in a further increase in this current. The net current is the difference between the dark current or the diode current and the photocurrent. And since these two currents flow in opposite direction, the dark current is actually a result of diffusion across the barrier, and the photocurrent is a result of drift across the barrier. And they flow in opposite directions, so that's why we have subtraction over here instead of addition of the two curves, of the two currents. Another kind of photodetector is a PIN photodetector, in which we have a p-type layer, we have an I layer, or intrinsic layer, and we have an n-type layer. In some semiconductor, this I layer actually means lightly doped layer. Like for example, in silicon, we can have an intrinsic layer, but in case of gallium nitride, for example, gallium nitride inherently or naturally has electron concentration around 10 to the power of 16, 10 to the power of 17 per centimeter cube. So in case of some semiconductor, this actually means a lightly doped layer, but generally we can assume it as intrinsic layer. So we got a p-type layer, an intrinsic layer, and an n-type layer. Once again, this works under reverse biasing, and we have a load resistor across this configuration to measure voltage across the photodetector. Now, there are a few advantages of the I layer, using the I layer in a photodetector. First, it gives us increased width for the photodetector. So the incoming light has got to deal with a wider area, resulting in the generation of more number of electron-hole pairs, leading to increased responsivity and increased quantum efficiency for the photodetector. And secondly, since we know that depletion width is inversely proportional to doping in a semiconductor, and since this layer is lightly doped, so it's going to result in a larger depletion width. And we also know that capacitance is inversely proportional to the depletion width. So larger depletion width means decreased capacitance, resulting in a decreased RC time constant for this photodetector, leading to higher speed for photodetectors. So PIN photodetector has higher speed, and it also results in higher quantum efficiency. Here is the energy band diagram of a PIN photodetector, and since it's running under reverse configuration, reverse biasing, so reverse biasing means connecting the positive terminal to the n-type layer. As I already told you that when we connect the positive terminal to any layer of the PN junction, their energy levels are actually dragged down. So the conduction energy level and the valence energy level of the inside would be dragged down. When photons incident on this photodetector in the eye layer, it's going to result in the generation of electron-hole pair across this energy band. It's going to transition from the valence band to the conduction band. Electrons would travel towards the minimum level of the conduction band, and holes tend to move towards the maximum of the valence band. The separation of these carriers result in a voltage across this configuration, and their movement results in a current. Here is another pictorial representation of a PIN photodiode. We got a p-type layer, an I layer, and an n-type layer. Electrodes are connected to both the p-type layer and n-type layer. And we know that under equilibrium, there would be diffusion of electrons from the n-type layer towards the p-type layer, resulting in uncovering of positive charges. And similarly, we would have diffusion of holes from the p-type layer adjacent to this metallurgical junction towards the n-type layer, resulting in uncovering of negative charges. So because of these, we would at this junction we would have negative charge density, and at this right junction we would have positive charge density. Now the electric field across this configuration would be 0 in the quasi-neutral region. It's going to start increasing. It would be maximum at this junction of the p-type layer, and I layer would remain constant across the I layer because we do not have any uncovered ions in the I layer, and it's going to be maximum once again at this edge. It's going to stay constant, and it's going to be maximum at this edge of the I layer and n-type layer, and would be maximum at this edge of the I layer and the p-type layer as well. When photons are incident at this surface on the p-type layer, and if the energy of the incoming photons is greater than the band gap of this semiconductor, they are going to travel to some distance inside the semiconductor. For example, assume they travel to a certain distance inside the I layer of the PIN configuration. So it's going to result in the generation of electron-hole pairs. Electron would travel towards the right because they are attracted by the positive terminal, and holes would travel towards the left. They are going to be attracted by the negative terminal. And it actually takes a particular time for the electrons to be collected by this electrode and for the holes to be collected by the left electrode, and that time is called the transition time. So towards calculating the transition time, let's perform some calculations before that. We know that the response time is limited by the RC time constant, where capacitance is equal to permittivity of the semiconductor time area divided by the width of the I layer in this photodetector. Similarly, the electric field across the I layer in PIN photodetector would be equal to the built-in electric field plus the electric field as a result of the reverse bias voltage, since we run this configuration under reverse biasing. Generally, this electric field as a result of the reverse biasing is much higher as compared to the built-in electric field. So we can assume that most of the electric field comes as a result of this reverse biasing, where E0 is the built-in electric field. Now, it's going to take a particular amount of time for electron to travel from this point towards this electrode to cross the I layer, and for the hole to cross the I layer and get into the p-type layer, and that time is called transit time, equal to the distance that these carriers travel divided by their drift velocity, and drift velocity is further equal to mobility of these carriers times the electric field. Drift velocity of both electrons and holes is a function of the electric field. According to this equation, drift velocity is equal to mobility times electric field. it's linearly proportional to the electric field up to a certain point, but at a certain critical electric field, the velocity of these carriers does not increase any further because of striking and scattering mechanism inside the crystal lattice. So assume this configuration of a PIN photodiode, assume that this is the I layer, and when photon is incident on this I layer, it will result in the generation of electron-hole pair. Now assume that the electron has to travel a distance of capital L minus small l to the right electrode, where L is the total distance or the depletion width of the I layer. Similarly, hole has to travel a distance of small l towards the left electrode. Now the time it takes for electron to travel from this point towards the right electrode would be equal to this distance, capital L minus small l, divided by the drift velocity of electrons. Similarly, the time it takes for holes to travel from this point towards the left electrode would be equal to this distance, which is equal to small l, divided by the drift velocity of holes. The time it takes for electrons to travel to the right electrode is called the transit time for electrons, and similarly the time it takes for holes to move towards the left electrode is called the transit time for holes. Let us perform some calculation for the transit time of electrons and the transit time for holes. Assume once again photon is incident on this PIN configuration, resulting in the generation of electron-hole pair at this point, and assume small l is equal to 5 micrometers. So assume this distance is equal to 5 micrometers. And assume the I layer width is 20 micrometers. So this entire width is 20 micrometers. It means that this distance travel by electron from its point of generation to the right electrode is 20 minus 5 is equal to 15 micrometers. So the hole has to travel 5 micrometers towards the left, and the electron has to travel 15 micrometers towards the right. How do we calculate its transit time? Transit time is equal to distance divided by the drift velocity of hole for transit time of hole, and the transit time for electron is equal to 15 micrometer, which is the distance traveled by electron towards the right electrode, divided by the drift velocity of electron. But the point is, how do we calculate the drift velocity for hole and the drift velocity for electron? So we need to go back to this plot where the drift velocity is a function of the electric field, but first we need to determine the electric field for that purpose. Electric field, as we know, is equal to the reverse bias voltage applied across this photodetector divided by the depletion width of the I layer of this photodetector, the width of this I layer of the photodetector. In this case, in the example, the reverse bias voltage is 100 volts and the I layer width is 20 micrometers. So our electric field is 5 into 10 to the power of 6 volt per meter. So at this electric field, we need to determine the drift velocity for holes and the drift velocity for electrons. So let's go back to this plot. Here is 10 to the power of 6, 2, 3, 4, 5, 10 to the power of 6. At 5, 10 to the power of 6, our drift velocity for electrons is around 10 to the power of 5 meter per second, and our drift velocity for holes is around 7 10 to the power of 4 meter per second. Replace these values into the transit time for hole and transit time for electrons. It gives us the transit time for both kind of carriers, which comes out to be 0.7 10 to the power of minus 10 seconds for holes, and the transit time for electrons comes out to be 1.5 into 10 to the power of minus 10 seconds. Here is an example on calculating the responsivity and quantum efficiency of a PIN photodiode. So assume a silicon photodiode with a cross-sectional area diameter of 0.4 millimeters. So from this diameter we can calculate the radius and cross-sectional area. The incident light wavelength is 700 nanometers and the incident light intensity is 0.1 milliwatt per centimeter square. The photocurrent generated is 56.6 nanoamps, and we are required to calculate the responsivity and quantum efficiency at this particular wavelength. Now we know that responsivity is equal to the output photocurrent divided by input optical power. Output photocurrent is given. How do we calculate the input optical power? Intensity of light is given. Diameter is also given. So we need to calculate the area and multiply it with the intensity of light, resulting in the input optical power. So responsivity is equal to IPH divided by P naught, comes out to be 0.45 amperes per watt. Now we got an equation for the calculation of quantum efficiency as well, equal to RHC divided by E times lambda. Replace all values in this equation, resulting in a quantum efficiency of 80% for this silicon-based photodetector at a wavelength of 700 nanometers. An important design parameter for PIN photodiode is the thickness of the eye layer in a PIN photodiode. How do you set the thickness of the eye layer in a PIN photodiode? So the key point here is the absorption coefficient. As we know that at shorter wavelengths we have high absorption coefficient, so shorter wavelength light is going to travel shallower into the semiconductor, but longer wavelength light is going to travel deeper into the semiconductor. So the thickness of the eye layer, and then we know that penetration depth or absorption depth is the reciprocal of the absorption coefficient, is equal to 1 over alpha. So the design parameter, the width of the eye layer in a PIN photodetector, actually depends on the wavelength of the incoming light. For example, if the wavelength of the incoming light is 0.9 micrometers, over here the corresponding absorption coefficient is approximately 5 into 10 to the power of 4. So the absorption depth would be 1 over 5 into 10 to the power of 4, or 0.2 10 to the power of minus 4, or it comes out to be 20 micrometers. In this calculation it's like 4 10 to the power of 5, but it's actually looking at the plot at 900 nanometers or 0.9 micrometers, it's around 5 10 to the power of 4. So the eye layer thickness in this case should be 20 micrometers. Now how about another wavelength? For example, assume a wavelength of I would say 800 nanometers or 0.8 micrometers. We get to this point where our absorption coefficient is 10 to the power of 5 per meter. So our absorption depth would be 1 over 10 to the power of 5, or 10 to the power of minus 5 meters, or 10 micrometers. So we need to set the eye layer thickness to 10 micrometers if the wavelength of our incoming light is 800 nanometers. This is going to result in like maximum efficiency for our photodetector. So the takeaway point is that the thickness of the eye layer in a PIN photodiode is it actually depends on the absorption coefficient at a particular wavelength, and it's an important design parameter. Another kind of photodetector is metal semiconductor metal photodetector. In this case, we have a semiconductor and we deposit 2 electrodes on top of this semiconductor. As we know from our theory of Schottky contacts, that assume an n-type semiconductor. If the work function of the metal is greater than the work function of the semiconductor, it would result in a Schottky barrier for electrons to travel from the semiconductor to the metal, and for electrons to travel from the metal to the semiconductor. So based on that theory, we can actually deposit interdigitated electrodes or any other configuration of two different kinds of electrodes, resulting in a metal semiconductor metal photodetector. Both of these electrodes would actually result in Schottky barriers at both ends of the energy band diagram. And the spectral range of this photodetector is actually determined by the band gap of the semiconductor, but also by the Schottky barrier. The spectral response range would be in the range of E times this Schottky barrier, and the upper cutoff wavelength would be determined by the band gap of the semiconductor. So the lower cutoff wavelength is determined by the Schottky barrier, and the upper cutoff wavelength for the MSM photodetector is determined by the band gap of the semiconductor. As I told you that this is a comprehensive topic, so let us stop at this point for today, and we are going to resume talking about photodetectors next week, inshallah. So that's it for today, and I will see you next time.